This is the fourth and final lecture for Text Unit 5, which is on heat and chemistry. This lecture is on finding heats of reaction from heats of formation. Okay, so first question naturally is, what is a heat of formation? A heat of formation is the heat of reaction, for which I've been using the abbreviation delta HRXN, for formation of 1 mole of compound from the elements that make it up. Okay, so what that means is it's the heat of reaction for a reaction with 1 mole of compound, like liquid water, on the right hand side, 1 mole. On the left hand side are the elements that make it up. Alright, water has hydrogen and oxygen, so I got a hydrogen here, 1H2, because that's how hydrogen is naturally found. And half a mole of O2, because we can do that in these type of thermochemistry studies. We can have a half mole of a reactant. Delta H for that reaction is negative 286.0 kilojoules. Therefore, the heat of formation of water is negative 286.0 kilojoules. That's what heat of formation means. Okay. By definition, the heat of formation for any element in its standard state is 0. And that's you'd have, for example, and that's because you would have, for example, if you think about oxygen, you'd have a mole on the right-hand side, and you'd have a mole of the oxygen on the left-hand side, because that's the element oxygen is made of. There'd be no reaction. That's essentially no reaction, so no heat. For any element in its standard normal state, therefore, the heat of reaction is 0. Alright, what are these for? What's the point of a heat of formation? Oh, by the way, and again, this is the symbol for a heat of formation. Any reaction can be imagined to occur in steps where the first step is formation of elements from the reactants. In other words, we tear the reactants apart into the elements. And the second is formation of product from all those elements. In other words, then the elements combine back into product. If we imagine any reaction taking place that way, the heat of the reaction would be the heat of formation of all the products. That's the final step. And the first step, where all the reactants are broken apart into elements, that would be the negative heat of formation of all those reactants. So we would take away the heat of formation of all the reactants from the total. So the heat of any reaction, to summarize or restate, is the heat of formation of all the products and the heat of formation of minus the heat of formation of all the reactants. That's what heats of formation are for. Right. Now, heats of formation, well, hold on one moment. Beg your pardon, I had a bit of bad editing down here at the bottom. Right. Heats of formation are tabulated for many species. See the course handouts. Now, more on that on the next slide of the presentation. Now, these handouts that are on Blackboard are actually drawn from these two websites. You'll see this one on Blackboard as Heat of Formation Tables 1. Many substances also appear in this file. This is on Blackboard as Heat of Formation Tables 2. Table 2 is the big one. There are many more things in Table 2 or in Table 1. Values for the same substance in different tables should be essentially the same. So if you need to look up heats of formation in a table, you look at two different tables, you should see essentially the same value for whatever substance you're looking at. Now here's an example problem, and I have taken heats of formation from heats of formation table 1. I've got the heats of formation of CO, H2O, and CH4. Right, notice the units of heats of formation from these tables are written as kilojoules per mole. Alright, now from these 3 bits of information, we can find delta H for this reaction. CH4 and 2 O2s goes to CO2s and 2 H2Os. Heat of reaction is heat of formation of all the products minus heat of formation of all the reactants. So, first thing I do is take all the products. In the balanced equation, there are 2 moles of water. This unit is important. We multiply that by the heat of formation of water in kilojoule per mole. Oh, notice I have the phase liquid marked here, or physical state liquid marked here. This is important because the heat for forming liquid water and the heat for forming steam, gaseous water, are different. In this case, I take 2 moles multiplied by kilojoule per mole. Units of moles cancel, and I'm left with a number in kilojoules. There's 1 CO2 among the products, so I take 1 mole and multiply that by the heat of formation of CO2 in kilojoules per mole. Moles cancel, and I'm left with a number in kilojoules. And then I can add these up, and I obey the addition rule for significant figures when you do that, and get a total of negative 965.17 kilojoules. Okay, now again, this is the total for the products. Okay, now this process gets repeated for the reactants. I'll show that on the next overhead. All right, our reactants are CH4. We have 1 mole of those. So I multiply 1 mole by negative 74.81 to get negative 74.81 kilojoules. And then we have O2, 2 moles of O2. However, this is an element in its normal or standard state, and therefore its heat of formation is 0. So this thing gives us a big 0. The total for the reactants is negative 74.81. Right. Then we take products minus reactants. Heats of formation of all the products minus all the reactants. That's negative 965.17 for the products. When we subtract the reactants, we subtract a negative number. That gives us a positive number. Negative 965.17 plus 74.81 is negative 890.36 kilojoules, which is the correct value for the heat of this reaction. Alright, you try this one. Find delta H for this reaction. Use table 1. Note sugar, C6H12O6, is in the organic section. Be sure to use heat of formation, delta H sub F, and not what is the actual heat of combustion, delta H sub C, or any other value that appears in the table. Alright, go ahead and download the table from Blackboard or the link. If you haven't done that already, have a look, attempt the problem, and then move on and look at the solution. Alright, products minus reactants. Here I just present the numerical solution. Here, allow me to bring the balanced chemical equation onto this slide. There it is up at the top. Okay, so delta H for the reaction is delta H for all the products minus delta H for the reactants. Alright, on the product side we have 6 CO2s and 6 H2Os. If you look at your tables, 6 CO2s is 6 moles times negative 393.51 kilojoules per mole. Then we have the water the contribution from the water, 6 moles times negative 283.5.83 kilojoules per mole. So, all this, beg your pardon, all this is the contribution from the product side. All right. After that, take the negative heat of formation for everything on the reactant side. Right, that's 6 oxygen. So we subtract 6 moles times a 0 again because oxygen is an element. And then for the sugar, we subtract 1 mole times, because there's 1 mole in the balanced equation, times negative 1268 kilojoules per mole. All right, so you have, I've separated them now, the products, and down here minus the reactants. Okay. Notice these notice these coefficients in balanced chemical equations are exact numbers. So, multiplying by the number of moles does not change the number of significant figures in the products. Then you sum them using the addition rule and significant figures to obtain the solution. Again, the numbers we collect and add are found by taking the products and subtracting terms for the reactants. All right, here's another. Calculate the enthalpy of combustion of alcohol. Alcohol is C2H5OH liquid. Here's the combustion reaction, which results in which it reacts with oxygen, beg your pardon, to make CO2s and H2Os. All right. Use table 1 to attempt this problem. All right, allow me to bring the balanced chemical equation over again. And here is delta H from the reaction. All right, first we take the products. We've seen this, this looks very similar to our previous calculation. Coefficient, exact numbers again from the balanced chemical equation, are multiplied by heats of formation from the table. 2 moles for CO2, 3 moles for H2O, and those two terms give us the products here. 2 times this plus 3 times this. Right, then I subtract, I've got it down here in braces, the term in the bottom. 1 mole times the heat of formation of the alcohol, because we have 1 mole of alcohol. And 7/2 times a 0, because oxygen's an element and therefore a 0. Products minus reactants, and we're taking the negative of a negative number again, notice that, gives an answer of negative 1366.82 kilojoules. Right. Now repeat this process for the combustion of ammonia, balanced chemical equation shown here. Given the following standard enthalpies of formation. Okay, note that this formation is combustion is to form liquid water, not gaseous water. I had to correct it. I had to correct a typo there. And I present these heats, or standard enthalpies of formation, as they're sometimes called, down here. Okay. Attempt this before moving on to the solution. Alright, here's the reaction again. I can write delta H as products, 4 moles for the NO2, plus 6 moles for the liquid water. Again, units of moles cancel, we're left with kilojoules. Down here, I subtract the term for the reactants. Notice once again, we have to take the negative and negative number in these calculations. And there's no contribution from the oxygen in these combustion problems. And that gives us this delta H of reaction. Which should actually be carried to the 10th place. My apologies, the 1st place. Alright, this is the conclusion of the final lecture of Unit 5.